We're diving straight into bidirectional normalizing flow, from data to noise and back. It's a paper from Liu et al. At MIT and Tsinghua that is really rewriting the rules for a whole class of generative models.
It really is. The model they introduced, BiFlow, it challenges this core constraint that has held back normalizing flows, or NFs, for decades.
And what's that core idea?
The big realization is this. The reverse process, the part that actually generates the image, it no longer needs to be the exact mathematical inverse of the forward process.
That is the game changer.
Yeah.
So they're decoupling them, training a separate model to be just an approximate inverse.
Exactly. And that freedom lets them use these really flexible, super efficient architectures like bidirectional transformers and achieve something incredible: single function evaluation generation. One step.
And the results speak for themselves. On ImageNet 256 by 256, BiFlow gets a state-of-the-art FID score for NFs of 2.39.
But the speed, that's the headline. We are talking up to 2 orders of magnitude faster, nearly 700 times faster on a TPU compared to the best autoregressive baselines. This is the moment NFs get serious.
Okay, let's unpack that because it's a huge claim. To understand the breakthrough, we need to set the stage. Normalizing flows have always been this, mathematically elegant idea, but they were stuck in the slow lane.
Right. So, at their core, NFs are about this perfect bijective mapping. You have a forward process, let's call it F, that takes your data, say, into X, and it carefully transforms it into simple Gaussian noise, Z.
And then the reverse process, F inverse, is what does the generation. It takes that noise and turns it back into a new image.
But the key constraint, the thing that caused all the problems, was that the forward process had to be explicitly invertible.
So every single step had to have a perfect, knowable reverse step.
Precisely. And because you train these models with maximum likelihood estimation, you need to be able to calculate the Jacobian determinant of that transformation. It has to be computable and tractable.
And that's what handcuffed the architecture.
Yeah.
Right? You couldn't just throw a powerful vision transformer or a UNet at the problem.
You couldn't. It forced everyone into using these very specialized, very constrained architectures, like coupling layers. You were designing for mathematical purity, not for raw performance.
So even when people tried to modernize them, like with TARFlow, which used transformers, there was a catch.
A huge catch. To keep that invertibility with a transformer, they had to break the process down into this incredibly long chain. We're talking thousands of sequential steps.
And that meant generation was causal.
Yes, causal decoding. It's like generating an image 1 pixel at a time, where each new pixel depends on the one you just generated. You can't parallelize it. It was a total inference nightmare, just 1 step at a time.
So just painfully slow. Makes sense.
That is the exact bottleneck that BiFlow just completely demolishes.
So let's get into the BiFlow innovation. They keep the forward model, the flow F, and they still train it like a classic NF with MLE. But the reverse side, that's where everything changes.
The reverse side is now a totally separate learnable model. Let's call it the generator, G. And its only job is to approximate the inverse of that forward flow.
So by throwing out that need for a perfect analytic inverse, the generator G gets all this architectural freedom.
All of it. And what do they reach for? The most efficient tool there is for this kind of thing. A non-causal transformer with bidirectional attention.
Of course. Because it no longer has to worry about those step-by-step dependencies. It can process all the noise at once and generate the image in a single parallel shot.
And that is why we're seeing these insane speedups. It's a fundamental architectural shift.
So the training is a 2-stage process. First, train the forward flow F, then freeze it, and then teach the generator G how to go backwards.
Correct. And that second stage, teaching it the inverse, is way more nuanced than it sounds.
I was going to ask about that. If it's just an approximation, doesn't that put a ceiling on the quality you're trading mathematical perfection for?
That's a fantastic question, and it's what the paper really digs into. What they found is that the flexibility you gain from approximating the inverse is actually much more powerful than the rigid certainty of the exact one.
So how do they teach it? I know they tried 3 different methods.
They did. The first and simplest was naive distillation. You basically just give the model the starting noises and the final image X and tell it to figure it out with a simple L2 loss.
That sounds really under-constrained. Not a lot of guidance there.
It's not. It's too weak a signal. So then they create a second method, hidden distillation. This is where you use the entire forward path for supervision, step by step.
Okay, that sounds better. More guidance. But there was a problem there too, wasn't there?
A huge one. The intermediate states in a flow model often have the same shape as the input image. So with hidden distillation, you're forcing the generator's powerful, abstract, hidden features to constantly be projected back down into pixel space at every single step.
You're crippling its ability to learn high-level representations.
Exactly. You're forcing it to think in pixels when it should be thinking in concepts. And the results showed it. That method performed the worst, even worse than just using the old exact inverse.
Which brings us to their solution. Hidden alignment. What makes it different?
Hidden alignment is the best of both worlds. It still uses the full trajectory for supervision, but it's smarter about it. Instead of forcing the generator's internal hidden states, the high, back down to image space.
Let me guess, they introduced some kind of adapter.
Pretty much. They use these small, learnable projection heads. Think of them as flexible translators. They learn how to align the generator's rich, abstract internal state with the corresponding state from the forward path.
So the generator gets to keep its powerful internal features, but it still receives dense, step-by-step guidance.
Precisely. It's a soft handshake, not a rigid constraint. And the proof is in the pudding. The learned approximate inverse actually outperforms the exact analytic inverse. Flexibility wins.
That's a fascinating result. But I remember a technical detail about norm control. What was that about?
Right. So even with F being frozen, its intermediate states can have these wild fluctuations in magnitude in their norm. Some steps have huge values, others are tiny.
Which would make the loss function unstable? It would only pay attention to the big numbers.
You got it. It creates a really imbalanced learning signal. So they did two simple things. They clipped the parameters in the forward model to stop the norms from exploding, and then they normalized the generator states before the alignment.
So it learns the relationship between states, not just their raw size. Very clever.
A simple but critical stabilization trick.
Okay, so they've decoupled the flow. The next big thing was getting rid of all the extra baggage. Let's talk about denoising. Other top-NF needed a separate cleanup step, right?
They did. You'd generate a sample, but it would be a bit noisy, so you'd have to run this whole other score-based denoising model on top of it.
It sounds expensive.
It basically doubles the inference cost. You
Right.
need a whole extra forward and backward pass just to clean up the image. It's a massive bottleneck.
And BiFlow just builds it in.
They just build it right into the generator G. They add one extra block at the end that's dedicated to denoising. So instead of learning to map noisies to noisy data, it learns to map noisies to clean data X, all in one shot.
So they go from 2 steps, generate then denoise, to one single efficient step, clean generation.
And it saves a ton of computation, about 15.8 times the flops, according to their calculations.
They did a similar thing for classifier-free guidance, or CFG, which is another classic speed killer.
For sure. Standard CFG is essential for quality, but it forces you to do 2 forward passes at inference time, one with the condition and one without. It makes you do 2 NFE sampling.
Again, doubling the cost.
But BiFlow's solution is so elegant, they just bake CFG right into the training process. The reverse model is conditioned not just on the class label, but on the CFG guidance scale itself.
Ah, so the generator learns to handle guidance inherently.
It does. And the result is that you get all the quality benefits of guided sampling with only one function evaluation. And you can still tune the guidance scale after training. They effectively cut the cost of high-quality generation in half again.
It's just optimization on top of optimization.
It really is. They fix a core problem, pick the right architecture, then just relentlessly stripped out every last bottleneck.
And the final numbers are just stunning. When you put BiFlow B2, their 133 million parameter model,
up against TARFlow XL2, which is a monster at 690 million parameters, BiFlow isn't just faster, it's flat out better. An FID of 2.39 versus 4.54.
better, 5 times smaller, and orders of magnitude faster. Just to say that speed number again for everyone, the broad generator speed up is between 60 times on a GPU and almost 700 times on a TPU.
It really puts NFs back on the map in a big way. If you look at the whole generative landscape, BiFlow isn't just the best normalizing flow now. It's competitive with the fastest models of any kind. GANs like StyleGAN XL, distilled models like MeanFlow.
And they make that great point in the paper that the model is now so fast that the VAE decoder has become the new bottleneck.
It's a problem flow researchers have only dreamed of having.
And this whole structure, this learned bidirectional map, it unlocks some really cool practical editing abilities right out of the box.
Yeah, let's talk about inpainting. Because you have that forward map from image to noise. You can take an image with a hole in it, run it forward.
And get the noise representation for that specific image.
Right. And then you just throw away the noise corresponding to the hole and replace it with new random noise. Then run that modified Z back through the generator in a single pass.
And because it's one shot, it's super fast.
Incredibly fast. And it fills in the hole coherently. The other example, class editing, is even more impressive.
This is where you just change the label, right?
Exactly. You take an image, get its noise Z, and you hold that Z's constant. But when you run it through the generator G, you just give it a different class label.
And what's so wild is that the image keeps its overall structure. The pose, the background, all that stays the same, but the object itself changes.
The examples are amazing. A hen becomes a flamingo. A tennis ball turns into a golden retriever, all from just changing one part of the input condition. That's the power of having this explicit learned mapping.
It really proves that the old constraint, the exact analytic inverse, was just a burden, an unnecessary one. BiFlow really has transformed NFs from a theoretical curiosity into a competitive, fast, and flexible tool.
It's a huge shift. You now have these two big ideas in flow-based models. You have the BiFlow approach, which is all about learning the forward path, and then you have modern flow matching, which uses a pre-scheduled path, often borrowed from diffusion.
Both are chasing that one NFE dream. But what BiFlow shows is you can stick to the core NF principle of a learned likelihood and still achieve incredible speed, maybe even get the best of both worlds.
Which leads to a really interesting question.
So here's something to think about. Now that normalizing flows have finally solved their speed problem, where does the real advantage in generative modeling lie? Is it in the carefully pre-scheduled diffusion-style flows? Or is it in the flexible, fully learned bidirectional flows that BiFlow has pioneered? And what kind of crazy hybrids might we see emerge when these two powerful ideas start to blend together?